I'm going to stop thinking any of them are straightforward or easy.
Yeah. Okay, so today we're going to finish this chapter 2. We've got a couple of topics to discuss. Pretty simple. And tomorrow there's a problem set, right? And oh, by the way, tomorrow we're going to do this a very well-known transducer called a geophone. It measures seismic vibrations, and the idea is really simple. But we're going to go through a complete analysis. There's just 2 problems tomorrow, and this is one of them. And we're going to go through a complete analysis, and it's really revealing about the basic idea of transduction, electroacoustic transduction. It's a really good example. So we'll spend some time on that tomorrow. Okay, so the next topic here is efficiency. This is appropriate for drivers. And all it is just what you'd expect. It's defined to be, it's a dimensionless quantity defined to be the power delivered to the load divided by the input power. It's standard, idea of efficiency. And so this is going to range from 0 to 1, okay? Between 0 and 1. And usually what we're interested in here is near mechanical resonance. That's widely true for sonar devices. Almost always they're operated, sonar projectors or drivers, they're operated on resonance. So we're going to use our model piezoelectric transducer. And so the idea here is that this is a figure of merit, or it's a specification of a driver. And the question is, how do you determine it? And with a lot of transducers, you can theoretically calculate what you should be getting, right? But nobody believes that until you test it, right? And you know why they don't believe it? Because often the theoretical estimates can be way off. Something was missed in the theory. So the idea here is to determine this quantity. You've got a transducer and you want to determine it. And what we're going to do here, I mentioned this briefly before, we're going to see it more and more, is that with sonar device transducers, particularly in particular projectors, you can do simple tests in and out of water. Okay, water is where you ultimately want to use it, of course. Why would you test it in air? Well, air, compared to water, air is like a vacuum. Quantitatively, you can see that with the impedance, acoustic impedance. It's it's 3 orders of magnitude difference here. Much larger impedance in water than air. So almost always, I think, if you want to test a sonar transducer, a projector, okay, a driver, under the conditions of no load, what we call free, right? 0 force, a free, that's one of our important special limiting cases. You do it in air. You don't have to go to a vacuum. Technically, you should go to a vacuum so that the oscillating, the radiating surface there is not pushing against anything. But the difference, between air and vacuum here, compared to water, is very small. So air almost always suffices. So it's very convenient. So we're going to see, and it's very simple here, that by doing measurements in air and in water, and you'll be doing this in the lab in at least one experiment. Probably one experiment. You'll be doing this in the lab. We'll be using the tank room downstairs, 025, or now known as 25. They took the 0 off when they renovated the building. It was too expensive to put 0. So everyone got used to the basement being 0. So we're at the 100 level here, and then 200 the floors. I don't know, it just seemed nice, and now it's 25.
Second floor.
Well, yeah, it's really 025, right? I guess you get, like anything, you get used to it. But the old timers like me can't get used to it. When you get old, that's one of the problems with old age. You get so used to things. So I keep calling it 025 or 025. Why would you call it 025 rather than 025? Anyone? It's one less syllable, so you save time and energy. So it's not just a joke, you know. Think about it. It's part of our technological era, right? Is we're always trying to save time any way we can. Okay, so we'll be doing that down, and I'll remind you at the time. That's going to be done down in the tank room, and you'll be doing it in an in-floor tank. Have you guys been in there before? Okay. Okay, but not for a class, probably. Okay. Yeah, very convenient facility, and it has a tow tank in there too, where you tow something. So okay, and I've used that for research. So here we go. Here's our model circuit for piezoelectric, and again, you know, I'm asking to sort of, it's reasonable. I'm asking you to accept it now, and we will eventually explicitly prove it in one case, and we'll settle for that because you'll find that derivation is pretty challenging, but it's well worth it because we can actually, it's the one case where we can eventually derive this. This is not going to be really important for us. Remember, these are motional, these are electrical, this is fully electrical here when you see something like this. So these electrical values here are connected to the corresponding mechanical values by the so-called turns ratio, that N here. And now, we're not including the load in here. We played that game a little bit yesterday, but now we want to carefully distinguish between the free and the loaded case, okay? So this does not, we're not incorporating the load in here. So we're going to deal with admittance, simpler here. And if you look at the admittance of, here's the mechanical side. When we think about transducers, we separate in our heads, you know, an electrical side and a mechanical side, but almost always the actual physical device, they're intertwined together, okay? So think of it happens to some extent in a loudspeaker, it's generally true. So what's the admittance here of the mechanical side? What's the emotional admittance, or the admittance of the mechanical side? Well, it's 1 over the impedance, and the impedance of a series connection of impedance is just the sum of the impedances. So we take 1 over that. So in this case right here, the W denotes water. Here's 1 over the impedance. And we have these 4 elements here. In the air case, this is approximately 0. So we just zero out the load resistance and we get that. And the A will denote air here. Now, yesterday we mentioned, we actually didn't, I realized that we didn't prove this. And I don't think I've ever proved it. I'm surprised. But when you look at an admittance circle, well, I guess I can go to the next, yeah. When you look at an admittance circle here, it's near resonance, as we discussed yesterday. The diameter, this is approximately a circle in typical cases, and the diameter is related to the resistances, okay, to the total resistance here. So it's related very simply for an admittance circle. This resistance right here, the total resistance, here it's given by the sum of the motional and the load. Here it's just the motional because we're approximately zeroing out the load resistance. There's a simple, just 1 over inverse relationship between the diameter and the resistance. And I can't believe this didn't hit me until now, because I've taught this course a number of times, and now I'm thinking it might be interesting to go there and see that's readily proved. Some of this stuff can be difficult to prove. This can get to be really messy. I mentioned to you yesterday, I tried to prove that you get close to a circle, or close to it was just a nightmare. That's why I just went to the graph. I just took a special case just to be convinced that they weren't exact circles. So anyway, this is true. So we have these two different cases here, and these are going to be the diameters of the impedance circles for the two cases of air here, and then in the case where there's more loading, the water, I shouldn't say loading, the total motional resistance is greater here, so it contracts the circle. We can invert these relationships. So going along in the idea here that we're going to make these measurements, we can measure these diameters of these circles, so we can get the resistance for that. And you just have to invert. This is two equations and two unknowns. The resistances, it's easy to invert. And here's what you get. So once we know the diameters, we can get the resistances. Okay. Now, we're interested in the efficiency, right? And it's the power delivered to the load divided by the input power. The power delivered to the load is the I squared R. Okay, it's the current through the load times the resistance. This technically, it's not going to matter here, but technically this should be the RMS. This is the square of the RMS current, because we're interested in average power, of course. So this is not the peak current, right? It's all going to cancel here anyway. And then here's something that's interesting. I don't know if you've ever thought of this. Believe it or not, I had never thought of it. But on resonance, we need to analyze this circuit, and we're going to do it on resonance. What effectively happens to the capacitor and the inductor on resonance? Does anybody know? Either you know or you don't.
Cancel each other out.
Yes, yeah. And believe it or not, I'd never thought about that until I taught this course. And the impedances here are equal. It's easy to see that the impedances are equal and opposite. On resonance, this is 0, right? So they're effectively canceling each other out. In other words, the voltage drop across, the potential difference across here is always, through one cycle, always equal and opposite to the potential difference across there. So this is effectively just a short. And now we have a very simple circuit. Okay. We're including by the way, we're including the blockage resistance here just for generality. Typically this is going to, you can neglect that, but just to be more general. And it will come up in an experiment, I think, where you actually will see, you'll try to measure it, see if that is there, and I think it is there with a lot of uncertainty, but that's another issue. Okay, so getting back to this, here's what we've got. This is the power delivered to the load. And on resonance, we can forget the inductor and the capacitor, which is very simple. The current delivered to the load and this is just not just simple Ohm's law. The voltage across here is the same as the voltage across here is the same as the voltage across here. These are gone. So we just do Ohm's law to get the current in terms of the voltage. We want to get rid of that current, I sub L. So we get this, then we substitute this into here, and this is the power to the load in terms of the parameters of our circuit, the resistances and this driving voltage. So that's the power to the load. What's the input power? Okay, again, this is very simple because what we have here is just the power being delivered here. This is irrelevant. The energy is going back and forth here. So the average power that's delivered is what this source sees here is these two resistors. You simply add them, and then you have this side and this in parallel. So the equivalent resistance, the resistance seen by this source here, is very simple. And the 1 over the value, I've written it in here, 1 over the value, we add those two in parallel. We have the series resistances, and then because we have this parallel combination, the 1 over, they add in reciprocal. So this is the equivalent resistance seen by the source. And now we can find the power delivered by the source, V squared over R. So we get this. The efficiency is in the ratio. It's the power delivered to the load divided by the input power, and we get this expression. Now, this, I want to mention, it's mentioned down here, but I might as well mention it right now. This will be useful to you in an experiment, and I can't remember which one it is, but you'll want to use this. And the reason is, you know, the way this has been, the way it's stated in the book, and the way I've been presenting it here is, what we're going to measure, what you can measure is these diameters, these impedance circle diameters. And from those, you can get the resistances. So analytically, we can substitute these expressions in here and get an expression for the efficiency in terms of the diameters of the two circles and the blocked resistance here. Okay, so that's one way to approach this. A more modern way is to just dial up an equivalent circuit in the network analyzer, okay, and fit your measurements. Have the box fit your measurement. You know, find parameters of the equivalent circuit. And you guys actually did that last week, right? In a simple case. So it's pretty simple here too. So the more modern way of doing this, and what you'll do in the next experiment or the one after that, is you won't need to do this. You won't need to measure these diameters. A better way, I think it's more accurate and it's easier, is just to fit data to an equivalent circuit. And that way you'll get those, and then the equivalent circuit will give you these values here of the resistances. So you can just plug them into here. Here's another expression of it, somewhat simplified, multiplying through here, clearing the denominators here. So this is equivalent to that. So you'll be using this. You'll be using this in probably next week, but again, I can't remember if it's either the second or the third experiment. Now, when the blockage resistance dominates the other resistances, which is often the case, it becomes very simple here for the efficiency. It's just given by this expression. And you'll notice here, and I'll add to this, if you're interested in high efficiency, what do you need here for high efficiency? What do you want? So high efficiency is going to be you can think of this in two ways, either a big load or a small motional resistance, right? That's where you get high efficiency. Now there's a little bit of a problem here, is when, if this is high, then you're not going to be, there's not going to be much power. See, efficiency is dimensionless. It's the ratio of the powers. It's answering one issue. How efficient do you want this to be? Defined to be, you know, the power you get out compared to the power you put in. So when you go to this limit to get the high, if you're really interested in high efficiency, there's a price you're going to pay here. You're not going to get much radiation out, probably, unless you can make this really small. So assuming this is not very small, and you want high efficiency, the price you pay is you're not going to get much radiation out. But it'll be efficient, if that's what you care for. It all depends upon what you're after, right? And transducers, a lot of things, and especially transducers, is just some kind of balancing act. You want to just kind of overall optimize everything. You can't optimize every aspect. because there's a lot of interrelationships going on. So you just do the best you can overall. Okay, any questions about that? So we'll do some homework. The second problem, we'll do some efficiency calculations tomorrow, the second problem. I'm pretty sure they're in there. Now what we just did is good for drivers. Going the other way, when you have a sensor, almost always a sensor, which takes, in our case, acoustical energy and turns it into electrical energy. It's really not, it's true using energy there, but that's not really what we do and how we think about it. We're taking some acoustical energy here and we're converting it into a voltage, right? Almost always it's a voltage. And that voltage is when we analyze what we receive here. So in the sensor case, we have an acoustic wave coming in here. We're picking it up here. Almost always this is being put into some high impedance analyzer. So there's very little current, right? So the efficiency from this previous section that we just talked about is really kind of meaningless here. It's going to be close to 100% and it's really not telling you anything. Okay, it's really not giving you any useful information. So we need to look at this differently. And there is a more general way of looking at this. And it leads to what's called the electromechanical coupling factor. We've actually, I think, seen this before, but this is where we really semi-properly introduce it. It's this K quantity, often denoted by lowercase k. So that's what we're going to talk about now. And this is an important quantity. It comes up a lot, sonar transduction. Okay, so we're going to assume we have a reciprocal we're going to look at this from a basic physics point of view. And I want to warn you right away, almost all authors don't do this. The reason I know that is there's trouble with Brian's derivation here. He made some mistakes, okay? So, but it's still useful to go through, I think, and to see it. And I'll point out the problem here. So here's the idea. You recognize the canonical equations here for a reciprocal transducer. Same coefficient there. Here is an equivalent circuit. Not really a proper, it's part cartoon, part equivalent circuit, right? It doesn't have right units here. But it is, in a formal sense, this was the first of the 5, I think. Looks familiar? You can show with Kirchhoff's rule laws that you get this, okay? So, and it'll be sufficient for our purposes here. We don't need to go to the full electrical circuit. We can just use this. And we're going to take an energy approach. So what Brian's doing here is he wants to motivate the definition of the coupling factor. And most authors just plop it down. They just tell you, this is going to be a motivation of it. But like I said, there is problems that will hit immediately here. Okay, so we're going to look at work. This should be at. This on here, it should be at. We're going to look at the energy done here. The work done at the terminals. So on the electrical side here, the work over some time interval is going to be the integral of the power, and the power we can write as the voltage times the current, right? Well, yeah, but remember, all these quantities are in general complex because we have phase. We have to deal with phase here, obviously, right? Which you know well from just the previous course. So, and we haven't seen much of it here, but we will see it in transducers. There's phase differences are going to be involved, almost always. So we have to take, remember, we treat these variables here, like V and I, V and F, and U and I. We treat them as complex so that we can incorporate amplitude and phase together. But when you take the product of these two, they're actually real. And when you take the product here to find the energy, you've got to take the real parts before you do the product. Remember that? Remember that warning from, yeah, or you will get the wrong answer. So, this is a problem immediately, and everything is going to follow here. How do we get around this? Okay. So this is technically incorrect because these are complex numbers here. You've got to take the real parts. So I tried to fix this. Okay, when I first hit this, and there's a standard identity. It's very easy to prove. When you have two sinusoidally oscillating quantities, same frequency, and you want to find the average of the product of the real parts, which is just what we mean, what we're trying to do here, right here. Oh, and here's incidentally the work done on the mechanical side. It's instead of velocity times current, instead of voltage times current, it's force times velocity, right? Same thing on the other side. This is exactly what we want to find. So there's this trick. I don't know if many of you have seen it before, but people who do a lot of complex analysis associated with oscillations and waves all know this trick. You can forget this kind of somewhat tedious process here and just multiply the two things, but you've got to take the complex conjugate of one of them, and then you take the real part in the end. And due to the averaging, there's a factor of a half here. How many of you have seen this before? It's really simple, and you don't want to use it unless you do this a lot, you know. So we don't need it in this class. But I thought this would help save the derivation here, but it got really messy. When I tried to do this rigorously, you know, using, not just naively here, neglecting the fact that you got to take those real parts, when I tried to do that rigorously with this, it just became unmanageable. So what we're going to do is, we're going to assume that they're all in phase. In other words, they're all real, or they're all complex, but they have the same argument, okay? Everything's in phase here. Or they're all real, whatever, however you want to view it, doesn't matter. That's the only way that we can actually proceed, as far as I can tell. And like I said, I think I checked this in other books, but I couldn't find anything. So, Brian's book is more physics-oriented than a lot other Sonar transduction books, and that's the main reason that I chose it as the textbook. But you know, transduction is a difficult subject, and it's not all that rigorous. Okay, when you see mistakes like this, it's a pretty fundamental mistake, right? Okay, so anyway, let's just proceed along here, because it is, I think it is, we get something out of it. So what we do is, we take, to analyze this, we take the transduction equations, substitute these expressions for the voltage and the force into here. And that's going to give us 4 terms, right? Because there's 2 terms here. There's going to be, we got 2 terms there for V and 2 terms for that. We're going to get 4 terms. However, 2 of the terms are going to be the same. Because we have a reciprocal transducer, the energy going this way is going to be the same as the energy going that way. And you can see that. That's actually nice to see this explicitly. And I don't think we've come up with that perspective before. We've, I think, come close. But you can see it here. Whoops. So here's the purely electrical. When you make that substitution, you're going to get these 4 terms. Okay? And you'll notice these 2 terms are the same. Okay? So that's telling us that in a reciprocal transducer, it's got to be reciprocal, of course. These T's have to be the same. That the energy flowing one way is equal to the energy flowing the other way. So we can combine them into that. Okay? And now, now let's integrate over, we want to deal with average, we're going to integrate over some time interval, and for it to be accurate, it should be an integral number of periods. And so, I'm just being a little bit careful here. You know that when you average the square of a sine wave, you get 1/2 the square of the peak current, for example, in this case. So here's what you've seen before. 1/2. I'm using the 0 subscript here to denote the peak value of the current. So when we do this, here's what we get on the electrical, purely mechanical. And then here's what we get for the energy flowing this way and that way. There was a 2 previously, so the 2 is canceled with the averaging 2 here. And we get that. It's averaging 1/2. Now we're going to write, this is a little confusing when you first see it, but we're going to now reintroduce the factor of 2. We're going to define this to be 2 W work, the mutual work. So the W mutual here is the work going in one direction. So because we have the total mutual work here is double that because it's the same going in opposite directions. So it's just convenient to define W mutual to be the energy going in one direction. And here it is. Okay, now I just want to point out to you that what's the physical meaning of this? The WE here, what's the physical meaning of this? Well, it's the, you can see it just involves the electrical impedance and the current. And what it is, it's the work when you block the mechanical side. Blocking the mechanical side means that there's no velocity here. There's no contribution to the current here. So we just get this. It's now become essentially purely electrical. These 2 cancel, and you just get that expression that we had down there. So you get this expression right here. So the physical meaning of this is that it's the work that's being done on the electrical side when the transducer is blocked. Similarly, this is the work on the mechanical side when the circuit is open, electrically open. So you don't have to worry about that other current there. Okay, and we just discussed this. Yeah, we have this. Yeah, maybe this is a better way of thinking. We have a WEM and a WME, but they're both equal here. And we've defined those to be the mutual work. So, here's the definition of the electromechanical coupling factor. First of all, it's very important for you to recognize here, it is a dimensionless number. It has no units, okay? It's a ratio. And it's defined to be the ratio of W mutual, the work going one way, divided by the other works. And to come up with to treat them on equal footing, we take they use the geometric mean here. Okay? I guess you could have used the arithmetic mean. That would get ugly. I can see that getting ugly. But it's defined to be the product of the 2, you take the square root. This gets you back to units of power, right? And it's treating these on equal footing, which we have to do because we have a reciprocal transducer here. So you can see that it's dimensionless, and if you substitute these quantities, these expressions here, and do a lot of cancellation, you end up with this. The transduction coefficient divided by the square root of the product of the electrical and mechanical impedance. Often people deal with the square of this to get rid of that square root. So this is how we'll usually deal with it. That's the square of the electromechanical coupling factor K. It's a dimensionless number of the amount of transduction. Okay? Based on the purely electrical and purely mechanical side, you're comparing it to that. So this gives you, the greater this is, the greater, some sense, fraction of transduction you're getting. You got a better transducer. There's more transduction taking place. Now, we did this all for everything being in phase, which means if everything has the same phase, you can imagine all these quantities to be real, okay? But it's true when they are complex, what people do is they simply define this to be this way. They define it to be that way, that the quantities are complex. But now that I think about it, usually when we deal with this, typically they're going to be real. There'll be no problem, I think. I'm not quite sure. But anyway, it's defined in general to be this. And as I said, I think most authors they just plop this down with no motivation. But it is good. You can see there's physics in the motivation here. It's just that it's plagued by this problem. You know, how do you do this in general? I don't know how to do that. I don't know. I thought this would save it, but it's just got, like I said, got to be too complex. Too difficult. I shouldn't say complex. Okay. Any questions so far? Okay, well, the next thing we want to notice here, this is part of why this is such a nice quantity, this dimensionless quantity, is I want to remind you the first lecture way back here, in the first lecture of this chapter, we went through, this was, okay, everything's linear, that's nice, cartoons, and then we had physically appreciated these quantities here, these impedances. And I didn't realize until this time through the course, these are impedances too, they're transfer impedances. And I don't think I realized that before, which I should have. Okay, these transduction coefficients. So these have all physical meanings when you look in limiting cases here of either blocked, no mechanical motion, or open circuit, no electrical current. And then we said, oh, by the way, unfortunately there's another few that are kind of mixed here. Okay, and these are involved, these are transfer impedances, these are transfer impedances here. No, I'm lying. This is a voltage, this is a current. These are not transfer impedances. But instead of looking at blocking, it's convenient to also appreciate the other limiting case, which is no load, no force, no load. And then if you analyze, this is not immediately obvious, but it's simple to show that you get this, and we talked about that. And now look, how can we write this now? Recognize this quantity. We're going to have, factor out a ZE. Go reciprocal and factor this out. And you get that, right? And what's this? Right. That's k squared. So this is useful for us. This is useful. That's one of the usefulnesses.
So
One of the. It's not really the same as uses. Well, anyway, let's not worry about that right now. Yeah. Pardon me?
it's okay.
Did I do that right?
Yeah, that's good. Yes, that's it.
Okay. So going back to wherever we were. Yeah. So now what I have done here, and previously we called that V over I for no force. Well, that's the input electrical impedance, so we should call it what it is. So we didn't do that back then, but so we call it a Z. It's the input electrical impedance. The capitals here tell you that it's electrical. All right, remember that? It's important. And similarly, this is all symmetric on the mechanical, looking the mechanical way, the mechanical side, where it's shorted rather than opened. So it's shorted. We have the same thing. So we can now write these expressions like that. Okay. Now, there's a little more here in the textbook. Now, let's go through this. Brian states, he just states it, that when you have a transducer, typically, and we've talked about this before, when we do, and boy, it took me a while to appreciate this. We do this theory, we're really thinking of a transducer. We're doing the theory of the energy going one way or the other way. We're doing it at the same time. Remember I've talked to you about this before? we're not often to do theory, we don't have to specify that it's a receiver or a transmitter or sensor or driver or whatever. We don't have to, we can go ahead and do the theory. That's very useful. We're unifying. It's a unification. And that's a big deal in physics, right? You guys know that, right? You know, electricity and magnetism for a few thousand years were thought to be separate subjects. And then they were unified in the 1800s. They all come from electric charge. They come from the same source. And people have now unified that with the what's so-called weak interaction, okay, another fundamental force. So the idea is to unify, there's really just one force in the universe. And it perhaps has evolved over time, the Big Bang. But a unification is a big deal for physicists. We want to make things as simple as possible. So why did I get into this? Oh, so the transducer, right. If we can view a transducer, you know, not have to specify which way the energy's going, that's very convenient. And then later, ultimately though, down the road, usually you're going to specify. Now I guess I have to clarify that a little bit. As you all probably know, there are sonar transducers that actually operate both ways, right? They can be operated, you know, not simultaneously. I think you switch back and forth, right? I don't know how you could, that would be an interesting trick. You know, I don't know if that can be done, but it's, even if it can be done, it's probably not practical, right? So you gate, or you go back and forth, right? Okay. So, right, okay. So here, following the textbook, okay, if we do specify which way the energy is going, whether it's a receiver or a transmitter, if it's not acting in this kind of superposition that we have here for convenience, then there's a simpler form for the square of the coupling coefficient, a more physical form. And Brian just states this without proof. It's the energy transduced divided by total energy input, which is very reasonable here, right? We went through this theory here where we had, in general, we had this superposition where we had energy input coming from both sides here. And there was a price to pay for that. We come up with something that's not all that physical, you know. But if it is just flowing in one way, so I think it's very reasonable. Proving it, though, is another matter. And if you try, I think I tried to prove this, and then I hit the same kind of problem that we had before, where it becomes really complicated. So what we're going to settle for here is a special case, and this is in the textbook, and it's embarrassingly simple. Okay, so I don't want you to. I want to lower your expectations here. Okay, so we start off. This is fine. There's no problem with this. This is a standard simple model of a piezoelectric transducer. We're neglecting the blockage resistance. No problem. Okay. So we're first of all going to first simplification in here. Oh, sorry. So we can think of this now as we can imagine that there's a load here. Okay. To get at the k squared here, to show this, to verify this relationship, we're going to look in the free case, so you can see it's free here. Okay. And now we can so we're going to derive this, okay, in a highly special case. So remember, this is true. That's what we're just talking about here. This is true, all right, and it's true really by definition of k. So it's absolutely true. We can find k squared because we're after this. We can solve this for k squared, and we get that. So the idea here is that in this case, we're going to find these impedances and show that we get this. All right? So to do this, and I think I tried it. I think I tried to do this in general, but again, it just gets really complicated. So we're going to make simplifications here. We're going to assume that the frequency is sufficiently small. When you have the frequency is low, what effect does an inductor have? Nothing, because it's acting on the change. It's inductive, using Faraday induction. So we can kill this. Okay. Now, with the frequency being low, it means the capacitor is going to start acting like blocking. It's going to reduce the current. Right? So we can neglect the losses in here. So at low frequency, both of these two things, we can forget both these two things. And you can derive that quantitatively just by looking at the impedances now that I think about it. You know, the impedance is going like 1 over the frequency here, so it's going to dominate. That's a mathematical way of doing it, okay? So now what we have is, yeah. You know, another way to simplify this would be to look at resonance, right? I think I did this in the past, but, well, anyway, let me think about that again. Oh, hold on, I want to make a note here. Anyway, following along with this, in the low frequency limit, we now have this very simple circuit. This is really simple. Like I said, I think it's embarrassingly simple. So this is C, the motional capacitance, right? Okay, so this is what we're going to analyze. It's greatly simplified from this, which is already simple. So, we're going to verify this in a highly special case. But again, on an absolute scale, I think it's good to do. In other words, it's better to do it than not do it. Sometimes you just have to look at things on an absolute scale, right? It's not very pleasing, but it's better than nothing. So let's do that. We need to compute what these are. What's the electrical impedance? Purely electrical impedance is we just have a capacitor here. It's 1 over I omega C naught. The input electrical impedance is what you see here is going to be the total capacitance, which is just, of course, because they're in parallel, the sum of the capacitances, right? So now we can form K squared, and we can simplify it, and we get this. And now the question is, does this equal the energy transduced divided by the total energy coming in over some time? Or you can convert it to power. Well, the answer is yes, of course, and here's how we do it. The energy that's coming in, the energy stored in the capacitors is going to be, energy in capacitors is 1/2 CV squared, right? It's a little bit like 1/2 MV squared for kinetic energy and mechanics. So we have a total capacitance here of the sum of the two capacitances, okay? The transduce energy is the energy just in the motional capacitor. So if you take the ratio of these two, if you take this divided by that, cancel the 1/2 V squareds, you just get this. So this shows us that in this very special case, we verified this, okay? An interesting question is it true in general? I don't know. My suspicion is no, but it's an indicator. This quantity serves as you can roughly think of this, but I don't really know. Okay. Oh, and there's finally, I think I might have already said this, but you can try to do this, more generally, and you just hit a lot of trouble. You hit a lot of trouble. That's an indication that it's not true in general. But I don't know. It may not be true in general, but I don't really know. But it doesn't seem to bother transducer people. Okay. Again, part of that's due to the fact they have a bottom line. You know, build the transducer, modify the transducer. And they got to get there. So being nice and rigorous and tying everything up and having a nice little theory, they don't give a lot of, put a lot of emphasis on that, okay? Because they got that bottom line. Okay, any questions? Okay, so tomorrow we do the famous geophone. And then another problem. And those two problems will take up the whole time.